everyone, I'm Dan. Wait, this isn't right. Hello everyone, I'm Dan, and yeah, I like this. So yes, I have heard you guys loud and clear. Where is this series? Is it just some ADHD-fueled single episode thing before disappearing off into the void? No. To be more specific, I actually have a job now. I'm the head of design and user experience at Torpedo Software. They're the guys who make Lua Learning, which means that, yes, I am helping to educate lots of young, aspiring developers all across the world, without ever having to attempt to teach a really horrible computer science lesson, which I can't really do. But the downside of earning money and generally contributing to the economy as a whole is that I don't really have as much time to dedicate to my other projects, and most recently that's been Fusion and Vanilla. This project has kind of fallen by the wayside as something I would really love to do, but which isn't quite so important right now. Nonetheless, there have been some developments in this project that I would quite like to tell you about going into this video. Namely, is that I'm moving away from Ash as our graphics library. For those of you who remember last episode, I originally went for the Ash library because it was a really nice Vulkan wrapper that basically just mirrored Vulkan's APIs into Rust. And while that was really valuable for learning Vulkan, I now no longer wish to use Ash. It's served its purpose in my mind. I've learned, and now I'm ready to move on to something a little bit better designed for Rust. Now, if you're already accustomed with computer graphics in Rust, you've probably heard of a library called WGPU. Or if you're more accustomed to computer graphics on the web, you've probably heard of an API layer called WebGPU. In fact, these two things are almost one and the same. WGPU is a Rust implementation of WebGPU. WGPU derives a lot of advantages from this setup. The fact that it's fully written in Rust means that it is completely compatible and really easy to use with Rust's ownership and borrow checking system, and the fact that it's based on WebGPU means that it's really easy to build portable stuff, which is a luxury I didn't quite expect to have. I thought that I would be committing to a specific graphics layer and then be done with it, but you know, if I ever wanted to make a browser-based version of my Voxel game, or God forbid I port it to iOS or Mac, well, now you can do that, because WGPU supports Metal as a backend. I'm going to be taking this opportunity not just to replace the graphics layer, but generally just to reapproach the project from a fresh slate, because I feel like very quickly with Vulkan I got bogged down thinking about incredibly specific technical details, and I kind of just want to toss away all of that Vulkan code and just restart again, make something that works before I try and make it work well. I think that's still a really common pitfall of the way that I do development, so I just want to avoid that this time. Anyway, it's getting pretty late as I record this, it's 22:45, so I'm going to go hit the bed, and when I get up in the morning, we'll see where we are with WGPU. Oh, and by the way, I am going to be leaving out a little bit more of the process this time. The first video was pretty much just about me being introduced to stuff, but from this point onwards, I feel like you guys wouldn't be super interested in that. I feel like you guys are much more interested in stuff that's actually relevant to the Voxel engine. So just expect it to be a little bit more snappy. Alright, so as you can see to the left of me, I have finished the WebGPU tutorials, at least as far as I care about them. So what we're going to be doing is we're going to be implementing a very simple voxel meshing algorithm. The way that this works is relatively rudimentary. We're not going to be doing any kind of greedy meshing or optimization at the moment. All we're going to say is, firstly, if it is not a solid block, then we skip rendering. We don't need to render anything for, like, you know, air. And then, if it is a solid block, what we do is we check each of the 6 faces to see which ones are visible. If the face is just pointing straight into a solid block, then it doesn't need to be rendered. But if it's pointing outwards into air, then we should render it because that's a visible surface. For each surface then, we're going to generate 2 triangles in order to create a square, and that square is going to be positioned on the face of that block. When you do this for all of the blocks in the world, you'll get a sort of surface mesh. It won't be the most efficient mesh of the surface of the world, but it will, at minimum, kind of work. For our cases where we just want to get some blocks on the screen, it will work just fine for now. This is all well and good, and it will work perfectly fine, except for one snafu, and that is that we've completely ignored how we're actually storing the blocks. While it's true that you could store every single individual block, typically we prefer to store them in 3-dimensional arrays, and typically you'll store something like block IDs. So you'll have like 0 is air, 1 is grass, 2 is dirt, that sort of thing. And you should be familiar with this because this is how Minecraft works. The other question to answer then is, how big are these 3D arrays? How many of them do we have? How are they distributed? And if you're making Minecraft Classic, the answer is simple. You just have one of them, it's the size of the entire world, and it stores all of the blocks in the world. And that's nice and simple. But it's also limiting, because now you have to store the entire world in one big block in memory. You can't unload parts of it, you can't make more of it. Generally, it's just not fantastic. So my plan then is to create a chunking system where I'll divide the world up into 16 by 16 by 16 chunks. That is 4,096 blocks per chunk, and they'll be positioned in 3D space so that we can just create a few chunks around where we want to create some terrain. If we ever want to create more in a certain direction, we can add more chunks in, and if we ever want to move away from somewhere, then we can delete the chunks just fine. But we're not out of the woods yet, because chunking introduces yet another problem. Remember when we're meshing a chunk, we need to check which faces are facing air and which faces are just facing into other solid blocks? Well, what do you do when you don't know what the block is facing into? I mention this because this is exactly the problem that chunks present. What happens when you have a chunk here and no chunk here, and you need to render a block that sits on the boundary? You don't know whether its outer face is visible. So for the time being, the way that I'm going to approach this problem is assuming that faces on that boundary between chunk and no chunk just don't exist, for 2 reasons. The first reason is that we're going to recalculate that mesh when the chunk comes into existence anyway, so whatever choice we make isn't permanent. And secondly is because these external faces are going to be very far away from the player, facing outwards into the void, and so the player is never going to reasonably see whatever we do anyway. So why spend extra effort generating mesh? Anyway, let's get right to implementing that. Alright, so as you can see, I've got my basic meshing algorithm done now, so we can actually move around, we can look around, and you can see it's a little bit glitchy at times where, you know, things go behind other things, because I don't have a depth buffer yet. But this is all able to be updated, so if I wanted to, I could like place and destroy blocks and remesh the world, and I would be able to send those updates over to the GPU and everything. It would be all good. So the next thing I think I'm going to work on is definitely getting that depth buffer in, and perhaps also getting some shading on the different faces of the blocks, making it a bit more memory efficient so I can handle larger worlds, because at the moment I'm doing this in a really inefficient way, which I really shouldn't. So I'm probably going to generate more of this geometry on the GPU side. So I'll catch up with you guys once I've done all of that. Alright, so now I've done some basic lighting work, and I've also done the depth buffer, so you can see behind this surface there are a bunch of other faces from behind the sphere, and when we look at the actual surface we're not seeing them through the surface anymore, so it's all working fantastic. And you can see the lighting, so on the east and west faces it's slightly brighter than the north and south faces, the top is brightest, and the bottom, which you can't currently see, is the darkest. This helps just define the shape a little bit more, so you're not just looking at a white blob, so that's pretty nice. But perhaps the most important change is under the hood. If we go to my code here, you can take a look. This is my meshing algorithm at the moment, and you can see I'm just pushing a bunch of these voxel vertexes. This is not like your regular mesh vertex, it's not just a bunch of floats and UVs and whatever. We're actually now looking to optimize the data we're sending over to the GPU. Now, I haven't quite done it yet. If you see here, we're just storing everything in a bunch of U32s. But my plan is to pack everything together to really make the most of the binary space available. And I think I can get it down to about 2 bytes per block, and that's with a little bit of inference from where the voxels are positioned. So the thing that's holding me back from finishing this vertex format and really getting it nice and compact is that we're not using chunks yet. Right now, this is a 32 by 32 by 32 scene, and the binary representation I'm thinking of using depends on chunks being 16 by 16 by 16. So I'm going to start working on chunks now, and I'll catch up with you guys when I have some chunks on the screen. Alright, so the chunk system is done, and I've done my GPU optimizations, and also I have a cup of tea. Very necessary, you must understand. But yeah, as you can see, these are bona fide chunks. They're all being rendered properly, they're all individual chunks. Every single one of those spheres is within a 16 by 16 by 16 separate array in memory, and they're getting rendered together into one scene, which is pretty cool. The way that I'm specifically achieving this is that every single chunk has its own bind group, which just stores data specific to that chunk that needs to be used for the rendering of all of the blocks. Right now that's just the chunk position, because we need to offset all of the vertices to position them where the chunk is, rather than positioning all of the chunks on top of each other, which is what it would do by default. So the bind group just contains the position, and that's all that it contains at the moment. But as for the actual vertices in the actual chunk meshes, they are now being actively optimized. So if we take a look in this mesh.rs in voxel vertex, you can see it is now just one U32, and this is packed data, so it's binary. And you can see here we're doing some bit manipulation. I actually have a Figma file open on the other screen here. So this is the vertex data format. You can see the first 4 bits store the X position of the block, the next 4 bits store the Y position, and the next 4 bits store the Z position. In addition to the position of the block, we also store the block face that the vertex belongs to. That takes 3 bits because we need to represent 6 values, which is up, down, forwards, back, left, and right. And that's actually all you need in order to fully specify that vertex, because we can infer stuff like UV coordinates and other stuff like that from the index of the vertex. So if we actually take a look in the shader code here, you can see we actually calculate what corner of the quad we're dealing with from the vertex index. Remember, there are 6 vertices that make up a quad, 3 for each triangle, and so using this information we can essentially assign a number to each one of the 4 corners. And that's what we're calculating here. We're just calculating what number corner are we rendering right now. And you can see we calculate quad U and quad V, which are our texture coordinates, roughly speaking. And we're just doing that with some more bit manipulation magic. And if we scroll down a little bit here, you can see vertex X, Y, and Z. We set this to the minimum corner of the block by default, and you can see we're also applying the chunk position at this point as well, which is coming from that chunk bind group. So here you can see we're switching on the facing bits that we stored earlier. It's the 3 bits at the end, and for each face we're essentially just moving the vertex into the correct position based on quad U and quad V. So not just texture coordinates, but also using it to define the actual shape of the face. And we're also doing some lighting as well by just setting a shading float, which down here in the fragment shader is just multiplied with the texture sample. Now, looking a bit closer at the actual chunk code, this is a bit messy and definitely going to get refactored down the line, but for now I just wanted something that works. So you can see each chunk stores its own position, it stores an array of blocks, it stores a mesh, it has a dirty boolean which basically just marks whether it needs to be recreated, and the chunk bind group, as mentioned before, which stores all of the rendering data that needs to be used for all of the blocks. So you can see I have a couple of utility methods here just for setting and getting blocks easily using vectors rather than using indices, because indices are nasty. You have my remeshing algorithm, literally the simplest thing in the world. I'm pretty sure I don't even need to explain it. The only thing I might need to explain is you need to have 6 vertices per face, but all of the vertices actually store identical data. So, that's kind of fun. And of course, right at the bottom here, we can see a world is just a hash map of chunks. There really isn't much to say about that. Here in the main code file, you can see when we're instantiating the world, we're essentially looping over a few chunk positions and we're creating chunks, we're generating the spheres and inserting them into the world, meshing them, whatever. All the initialization stuff basically. And down here in the rendering method, you can see we iterate over all of the chunks in the world. If the chunk has a mesh, then we set the vertex buffer to be the chunk's vertex buffer. We set the bind group to the chunk's bind group. And then we just draw all of the vertices. They're not indexed because they don't need to be, because we're dealing with voxel data and it's highly optimized already. Indices would just use up more memory. Anyway, I don't know if you can tell, but it's 22:41 right now. I've been working on this all day. I mean, it's really fantastic to see it coming along so quickly now. But also I'm tired and I have family to see tomorrow, so I'm going to go to bed and finish my cup of tea as well. It's lukewarm. Alright, so I've just spent today refactoring all of my code to really properly separate out the rendering stuff from the game state and generally make everything a little bit nicer to work with. And I've also made the camera controls a proper free cam, and so this required me adding mouse support and everything. But I do now have a proper input system and camera system and everything, so that's pretty cool. So let me show you what I've done on the code side of things. So as you can see, I now have this struct called gameState, which stores, as you guessed it, the game state. So that will include the contents of chunks, the position of any entities and stuff like that. Essentially, it's all the stuff that the game needs to store that isn't directly related to like graphics or like WGPU. Down here in our init method, you can see that we're making the game state here, but we're also making two other structs, one for surface state and one for render state. And this is specifically to do with winit and with WGPU. Starting off with surface state, you can see this is where all of the surface, device, and queue stuff has gone to live. Essentially all the stuff that serves as the interface between us and the GPU and the windowing system. Just like the really basic core stuff that has nothing to do with rendering pipelines. And then here you can see render state, which has all of our rendering stuff. So it has our camera uniforms, our texture bind groups, depth texture, render pipeline. But it also has a little thing called world renderer. And that's because I've actually completely separated out all of the rendering stuff from the game state into the render state. I need to have these parallel structs that represent the rendered contents of the world in parallel to the game state, which stores the actual contents of the world. So here's the contents of the world renderer. You can see it just has one method, and that is update rendered chunks. All this does is it basically reconciles its own chunk renderers here with the chunks that exist in the world. So if any chunks have been removed from the world, it will remove the chunk renderers. If any new chunks have come into existence, it will add those. And if the chunks are dirty, in other words, if they've had blocks added or removed, then it will remesh the chunk renderer. And then in here we have the chunk renderer, so this is where all of the chunk rendering stuff is now living, including all the stuff about packing vertices and like meshing and stuff like that. Now, I'll be perfectly honest, getting this to work was a nightmare because I originally had a very Java or C++ idea in my head of how I was going to lay out this code. But Rust is not Java and Rust is not C++. Rust has very strict rules about how memory is used, and so really I had to rethink the way that I was going to architect this. The chunk renderer is no longer tightly tied to a single chunk, instead it just borrows the chunk when it needs it and gives it back once it's done with it. That does mean that I am passing more arguments to stuff and not really storing like chunk references in structs and stuff. But I do think that is better because it is properly indicating to the compiler, I don't intend to use this except for this function call. So basically, I'm just learning to love passing function arguments and not being scared of long function argument lists, because all that is me being explicit about what the function needs that it cannot retrieve from inside of its own struct. Now, there is one problem that I just have not been able to solve with my current lifetime knowledge, and that's to do with this render pass here. So if we take a look at the lifetime signatures on the begin render pass function, you can see that we have this pass lifetime parameter. And that parameter is a real bitch to work with. I don't know why it's there. I'm not advanced enough to understand why it's there, but it is making my life misery because it means that I essentially have to define all of my render pass commands here. Like, I can't put it in another function, I can't put it in a method, I can't store it in the right struct. Like, I wanted to put this inner code here inside of chunk renderer because it's to do with the chunk renderer's internals. Then I wanted to put this for loop inside of world renderer because it's to do with the world renderer's internals. But instead, I just have to put it here because that pass thing, it basically makes it, if I add a function on a struct, then I have to set like that pass lifetime on the struct reference itself, which basically then just transfers ownership of the entire render pass into the struct and means that you can't call it in a loop or whatever. I just don't understand, and it's really annoying, and I'm kind of peeved about it, and by kind of I mean very. Though I guess eventually at some point I'll just be rendering into command buffers on a per chunk basis anyway, so this will be irrelevant. But right now it's annoying, and right now I really don't like it. But rage aside, can we just take a second to look at this code? So this is the chunk and the world structs that are stored inside of the game state. They are completely clean of rendering stuff now. And this is fantastic because it means that if we change rendering backends ever, or if we ever need to like reconstruct the rendering device, we're not going to nuke the entire game state, which is pretty great. Now, if you're a really keen-eyed viewer, then you will probably have already noticed an issue with my meshing code, and it's been in there for the past couple of days, and I haven't mentioned it yet, but I think I should, and that is that my chunk mesher only takes in the current chunk. And the reason why that's a problem is because the boundary faces on the chunk need to be meshed too, and those are facing off into other chunks. So we need knowledge of our chunk neighbors in order to fully mesh the chunk. Right now, I've really been avoiding the issue because my generated terrain has just been a bunch of spheres that conveniently don't touch the outside of the chunk. But if we want terrain to flow between chunks, then we are going to need to take into account our chunk neighbors when we do the remeshing. So I'm going to work on that now and get it all nice and working, and I'm going to change the example world so I can show you some terrain that's spilling over chunk boundaries, because right now I just kind of conveniently made it a bunch of spheres that just about don't touch. So I'll get on with that and I'll catch up with you on the other side. Okay, so just so we're clear on what the issue is, here is an example of where the meshing goes wrong. So this sphere is spanning multiple chunks, and you can see where the chunk boundaries are, the faces are disappearing. And that's because our current meshing algorithm does not have any knowledge of the other faces. It does not know that this chunk exists, and so it can't make any assumptions about whether there's air there or whether there's a solid block. So it just treats it as fully solid and doesn't render the faces. Now, this is perfectly fine over here, where the sphere is genuinely intersecting the void. But over here, where there is other geometry to query, we're going to need to be a little bit more considerate. So the solution that I've come up with in my code is to use this nearby chunks struct here, which you can see not only stores the current chunk, but also stores its 6 adjacent neighbors. Then it provides a few utility methods that allow you to turn a nearby position, that is, a position in any one of those chunks. It turns it into a proper chunk reference, and you can use it to get blocks and stuff. Now, the keen-eyed among you will notice that I'm returning a block ID when no chunk is able to be queried. Now, at first you might think that's a bit weird and that I should be using an option or something to indicate that there is no block here. But in reality, what I'm doing is a little bit more subtle, and this is something that the original blocks project also does. You see, I want to handle all blocks in a uniform way. I don't want to have special case code just because a block doesn't exist, because that's admittedly a very rare edge case. So instead of having special cases everywhere cluttering up my code, I've instead decided to use void blocks as a placeholder for when blocks have not been loaded in. Void blocks are fully like other regular blocks. If you spawned them in, you could place them down, walk on them, you could look at them. They would be actual proper blocks, albeit with a few interesting rendering properties like simultaneously being invisible and culling. The idea then is that any chunk that is not yet loaded in can simply return void blocks instead of anything else like air or stone or whatever, and that immediately signals to any code that's listening for it that this block doesn't actually exist. This is the void, this is not loaded stuff. But for any code that really doesn't want to care about it, it can just treat the void like it's made out of regular blocks, because it is. So stuff like physics collisions and stuff like that, well, that will automatically just work, because if you collide with void blocks, they'll stop you because they're solid. So you won't just walk out into the void and fall forever. As a result of these decisions, my meshing code looks really not that much more complicated. I mean, sure, we're now using this nearby chunks thing, but we've even managed to remove some of the conditional checks that we had before. We're just checking for air, which is now represented by the block ID 1, and solid blocks, which are represented by the block ID 2. Void blocks having a block ID of 0 will satisfy neither of these conditions and therefore not be rendered, but will still cull faces. And here in the world renderer, where we're creating this nearby chunks struct, you can see we're not currently passing in any information about the neighbors, which is why we're getting all the really weird meshing stuff. But this should be really easy to do. We can just pull it from the hash map, and we just need to re-render these chunks whenever the chunks around them get modified or changed or whatever, which shouldn't be too hard to do. Anyway, with all of that being said, here's what it looks like when the meshing is being done properly. So here we're actually passing in the adjacent chunks to the meshing algorithm, and you can see that it's finally filled in all of those faces, lovely, fine and dandy, whereas these faces that are properly facing the void are still being culled out correctly. If we take a look at the world rendering code, we can see we're just passing in references to the chunks that may or may not exist around the current chunk being meshed. The only change that we've really had to do is move this dirty flag into a separate for loop, because this requires a mutable reference to the chunks, whereas here we're taking immutable references, and you can't mix mutable and immutable references, because if a mutable reference changes something, then that's going to change what all the immutable references see, which makes them not very immutable. So there you go. So I was just editing that section of video and I realized that this has spiraled to be 22 minutes long. Originally I wanted to do some more stuff in this video, but it turns out that this video is just going to be about meshing and chunking. Who knew? I think we're in a pretty natural breaking off place for the video though anyway, because now that we have a proper chunking system and we have all of the meshing sorted out, we have a really good foundation to build upon. So I think next time we're going to start introducing new block types and terrain generation and stuff like that, and really start to round off this world system. Either way, I'd like to thank you guys for watching, and welcome to Stockholm. This is what it's going to be like. We're going to be working on a proper full-fat voxel game from scratch, and to be honest, I'm already having a wonderful time, and hopefully you are too. It's fun to do. But with that, I've been Dan, and I will see you guys next time. Hopefully fairly soon, but you never know, it might just be, a couple more years. We'll see how my motivation pans out.